What's up, guys? Um, I'm back here with another video. I hope y'all are doing well. As you can see, it's January 6th, and I just finished my first day of classes. Um, I didn't really have anything today besides biology and my research class that I'm doing, but um, tomorrow I have a lot. I have algos, system and networks, and intro to AI, which all are probably going to be a lot of work. Um, so I'm not looking forward to it that much. I'm also kind of tired, but it's okay. We'll power through. Anyways, I hope y'all have been doing well. As you can see, we're on. Or actually, I finished this earlier today. Um, I guess I can talk about my solution. So first, I did a simple approach where I simply traversed to the rightmost path. Um, but that wouldn't work, right? Because something like this happens, we can get from 1 to 3, but we can't get to 4 and 5 if we simply just go all the way down to the right, because it would end at 3. And I realized that we could use a level order traversal where we would take the last node on each level, and that's essentially what I had completed here. So um, I just did level order traversal, took a screenshot of the queue, if you will, and if the current number in the loop was equal to the last number, we knew that's the end, um, or the last node in the on the level, right? So I appended that to my resulting array and returned that. And I'm actually going to watch LeetCode's video on it real quick because I just want to see if he did it a different way or not. Let's go ahead and start with that. So we're over here.
Hey everyone, welcome back and let's write some more NeetCode today. So today let's solve binary tree right side view. The problem is pretty self-explanatory. We're given a binary tree and basically imagine you're standing on the right side of it. So this is the tree. Imagine we have a person standing over here, right? You can see from the right side, you can see everything on the right side. And so what nodes can this person see? Well, they can see the root node, right? There's nothing blocking that. They can see this node. Can they see 2? Well, you can't really see 2 because it's behind this node, right? It's basically blocking this node, right? And the same thing with these two nodes, right? We can see 4 because it's the rightmost, right? Like imagine the person sees this, but you can't really see that because it's being blocked by the 4. So when you just look at this example, this problem seems really easy, right? So your first thought might just be, okay, start at the root and keep going to the right? Just keep going down and we'll get the right side view, right? Every node on the right side. But we can make a counterexample pretty easily to show that that actually won't always work. Imagine this node 5 had a left child, right? Like let's say it has 7 over here. Now you can see that our result is going to be 1, 3, 4. We can't include these nodes because they're being blocked, but there's nothing over here, right? The 7 is not being blocked. So if this was our input tree, then our output would be 1, 3, 4, and we'd have to add a 7 to that because look at our person. They can technically see down here. So basically what this means is we can't only look at the right children, right? So you can actually solve this problem with a breadth first search. I know most tree problems you can just do depth first search, but this problem can actually be solved with breadth first search. There actually is a depth first search solution, but I'm going to explain the breadth first search solution to you because in some ways it's easier. And you might know breadth first search in a tree is also known as level order traversal. So it's also known as a level order traversal, which you're going to...
BFS is the same thing as level order? Huh. Okay. I never knew that.
See why it's called that just about now. So instead of saying that there's a person over here that can see only the right side of the tree, another way of framing this problem is saying, okay, for each level, right, each level of the tree, we want the rightmost node. So the first level, it's pretty easy because there's only one node. So we'll just take the 1 from that. What about this level, right? We look at the nodes together. For this level, we want the rightmost, so we get the 3. Next, we want the third level. And what's the rightmost value? It's going to be the 4, right? And lastly, we take the last level, and there's only one node. It's 7, so we're going to get the 7. So with a picture, this is pretty obvious, right? It's really easy to know what we're doing in the picture, but actually writing the code for level order traversal is a little bit tricky, and I'm going to show you how to do that. Basically, how we're going to implement this is with a queue data structure. So initially, what we're going to do is add the root node to our queue. So we're going to add 1 to our queue. And we're also going to have a result array. So now what we're going to do is take a look at our rightmost value in the queue. It's 1, so we're going to add 1 to our result. Next, now we're no longer looking at this node. We are looking at its children, basically the next level. So we can get that by taking the left and right child and adding them to our queue and removing the leftmost value from our queue. So we add the 2 and the 3 to the queue, and it's important that we do it in order, right? The left and right, the left has to be added first and then the right, because we always want to get the rightmost value when we, add to our result. So now this is the second level of our tree, right? So what are we going to do? Again, we're just going to take the rightmost value, in this case it's 3, add it to our result. And next what we're going to do is we're going to look at the leftmost value, pop it, right? But before we pop it, we want to take its children. Notice it doesn't have a left child, right? That's null, and the right child is 5. So we're going to take its children and add them to the queue. So now we're adding 5 to the queue. So we're done with 2. Next, we have to remove 3 from our queue because we're done with this level. We want to look at the next level. So we remove 3, but before we remove 3, we have to add its left and right child. Notice it doesn't have a left child, but it has a right child, 4. So we're going to add 4 to our queue. So now look at our queue. We have 2 elements, and these 2 elements represent the third level. So what we're going to do now is take the rightmost value once again in our queue and add it to our result, because that's the rightmost value in this level of the tree. And now we're going to repeat that process. So for 5, we're done looking at 5, but we have to look at its left and right child. It has 1 child, 7. So we remove 5 and we add 7 to our queue. And we also look at 4. So we're done looking at 4, right? So we pop it, but before we pop it, we want to look at its children. Notice both of the children are null. So basically and each just like contains what right elements from the previous. So once we've done that, and once this queue is empty, meaning we've gone through every single level of the tree, then all we have to do is return our result. So there it is. It's a pretty efficient solution.
Okay. Yeah. That's what I did. What are we? Count good nodes in binary tree. Hopefully this isn't too hard. Let's get some music. Just put out my other keyboard. Work, study, focus on coding. I just remembered I needed to put something on my calendar. Not sure what. actually currently on duty for RA, and I was gonna go to the gym, to be honest, and then come back and do this, but I have to stay here, which is unfortunate because I have a guy in a call in an hour, so I could have run, but hey, nose and blue are good. There's always a good note. Why is one not a good note? Oh, because the root is greater than it. I'm going to count the number then. And so I actually don't remember doing this problem at all. Acceptance rate, just crazy. This is a binary tree. Not a BST. Don't think we can do. I don't think we can do it iteratively. I think you definitely use recursion. Because you need to count all possible nodes. And I think this is DFS. I believe it is DFS. Okay. So if not how do I do this though? No nodes with a value greater than X. So if we go right, we compare 3 and 4, 4 is where we go. Oh no, how do I do this? If cur.val right? I don't think that's right. So the current value is cur.right. Oh fuck. If cur.val is great. If cur.val. So I have to check first. If cur.right and cur.val is greater than the cur.right.val, then what do we do? Increase res by 1. But this only compares the current value and the one next to it. I'm not gonna lie, I don't know how to do this. 1046. No one knows what the value greater than x. How do you do that? Hello? We can't use level order, can we? Oh my god, what was that trick with um the parent node and the children node is like the index is 2 times that and 2 times that plus 1 for the left and right. So what if we check? It's like 3 times, or this is index 0, so I guess 1 and 4. Wait. Oh, but you would have to start at, it would be 1 indexed. And you would check is 3 greater than 4? And then, fuck. It. Traverse the tree and constantly keep track of the current path maximum. Okay. Constantly keep track of the current path maximum. Oh, my back is so itchy. Constantly keep track of the current path maximum. Dang, bruh. Dang, they said it's easy. It's too easy. Fuck. Am I stupid? How do I keep track of a maximum of a path though? Like this. So if not her, then we return. Turn nothing. Ooh. Fuck. No, bruh, I'm just stupid. No. Oh, man. Fuck, I'm just stupid, I guess. Well, that's what I was going to do, but I didn't even realize I should keep track of my maximum. And I don't even know how to implement it. DFS cur largest, if not cur, then we return. Find out if this is greater than largest, then we can choose that one. I don't think this shit is right. Oh hell no. Oh hell no. I'm genuinely clueless. Okay. I'm gonna look at the solution. Fuck, I feel so stupid.
Hey everyone,
Oh my god, it's only 8 minutes.
welcome back, and let's write.
Bro, I swear, like, these were so much easier. No, man.
Some more neat code today. So today let's solve count good nodes in a binary tree. This is a
It might be the first time everyone's saying it should be easy. Oh.
welcome back, and let's write some more neat
10
code today. So
10K
today
3 years ago.
let's solve
Dang.
count good nodes in a binary tree. This is, according to LeetCode, this is Microsoft's most asked question of 2021 so far. And in my opinion, it's actually a pretty good problem to understand. A lot of good fundamental knowledge can be gained from this problem. So we're given the root of a binary tree that is going to always be non-empty. We want to count the number of good nodes in the tree, and a good node is defined. So for example, take node X. It is defined as a good node if, for example, let's take this node 4. If from the path from the root node all the way down to this node, this path in particular, if there are no nodes in this path that have a greater value than this particular node. So basically along this path, if there isn't any value larger than 4, then this node 4 counts as a good node. What about 1? Let's take the path from the root to 1. Are there nodes greater than the value 1 along this path? Yes, because good node. What if this here all the way down to this node, this path in particular, if there are no nodes in this path that have a greater value than this particular node. So basically along this path, if there isn't any value larger than 4, then this node 4 counts as a good node. What about 1? Let's take the path from the root to 1. Are there nodes greater than the value 1 along this path? Yes, because this node 3 is greater than this node 1, so then 1 is not a good node. So we can solve this problem in linear time, big O of n time, where n is the number of nodes, and memory complexity is going to be log n, or in other words, the height of the tree, which technically could be greater than log n. It could be as big as n. And we can accomplish this with a simple tree traversal. In particular, we're going to be using pre-order traversal. Reversal, meaning when we recursively run DFS on this, we're going to process each node before we do recursively the left subtree and recursively the right subtree. So the first question is the root node technically a good node? Well, this is basically the root node technically the right subtree. So the first question is the root node technically a good node? Well, this is basically the entire path. Are there any nodes greater than 3? No. So technically, yes, the root node does count as a good node. So what we're going to do now, we found one good node, and now we want to know how many good nodes are there in the left subtree and how many good nodes are there in the right subtree. Well, first let's do the left subtree, even though we could do it in the opposite order, but I'm just going to do the left first. So to count how many good nodes are in this left subtree, first we have to run the DFS on the left child. But before we do that, we have to pass to this left child. We have to pass what's the greatest value we have seen so far. We don't have to pass all the values we've seen so far. We just have to pass the greatest, because then we're going to check for every node. Is the greatest node that we've seen so far somehow check for all the values we've seen so far? We just have to pass the greatest, because then we don't. First, let's do the left subtree, even though we could do it in the opposite order, but I'm just going to do the left first. So to count how many good nodes are in this left subtree, first we have to run the DFS on the left child. But before we do that, we have to pass to this left child. We have to pass what's the greatest value we have seen so far. We don't have to pass all the values we've seen so far. We just have to pass the greatest, because then we're going to check for every node. Is the greatest node that we've seen so far somehow greater than this node? If it is, then this is not a good node. So to this node, we're going to pass the value 3. We're going to now process this node greatest, because then
in the path from the root. Oh. I still don't think this is right. Yep.
We're going to check for every node. Is the greatest node that we've seen so far somehow greater than this node? If it is, then this is not a good node. So to this node, we're going to pass the value 3. We're going to now process this. The greatest we've seen so far is 3.
How do you keep track of that?
1 is smaller than that. This is not a good node. So this does not count, but we still have to recursively run DFS on the left and right. Now, when we do run DFS on the left, obviously it doesn't have a right subtree, but on the left subtree, what value are we going to pass here? Well, we would want to take the max of 3, which was the parent's max, and the value here, of course, 1 is smaller than 3, so we're going to pass 3 to this node as well. So far the max we've seen is 3. Is the max greater than this node? It's not. So even though they're the exact same value, this still counts as a good node. So that's what we learned. And so Now we have seen 2 good nodes so far. Now the same thing we're going to do on the right subtree, literally the exact same thing, just recursively doing the same thing. We're going to pass 3 to this node because 3 is the max value we've seen so far from the root, right? If there was a really big value here, we wouldn't want to transfer it to the right subtree, but we're counting from the root downwards. So let's look at 4. Is this max value greater than 4? It's not, so then 4 does count as a good node. Now let's do the same thing for the left subtree. But when we go to the left subtree, we're not passing 3, we're passing 4 because so far now along this path, the max value we've encountered is 4. So we're going to pass 4 to this child node 1. Now obviously 4 is greater than 1.
Off by 1 error. Spanish doesn't get into me. But it's so good. Oh, it's spicy. Where's that off by 1? Ah, fuck. Alright, I'm back. Ooh. Dang. That one was spicier than the one earlier. Fuck. Why can't people just fix off by 1 errors like this? Oh fuck. Oh, I think it includes the equal. Right. Oh, close. Fuck. How do I not know the intuition behind this? So when people say go down a path, this is recursing until we hit this statement. Okay. That does make sense. Oh. What's wrong with this? Don't kill me. Oh, negative. But then this wouldn't work. Here. Oh, it would. Because if it's greater than or equal to, then we would add one. Holy shit. That shit was not. Why the fuck was it not working? Alright, why is it so slow?
1, so this does not count as a good node. Same thing on the right node. We're going to pass 4 down to this node. The max we've seen so far is 4, but this value 5 is greater than it. 4 is not greater than 5, so this counts as another good node. So altogether, you can look, we have 1, 2, 3, 4 good nodes, and we would, from the root, what would we actually do? We'd say, okay, so far we found one good node at this root in the left, right, plus left. This is basically the equation we're going to use, 1 plus left plus right. Of course, left is actually going to be 1 because there's one good node in the left subtree. Right is at far we found one good node, and we're going to use 1 plus left plus right. Of course, left is actually going to be 1 because there's one good node in the left subtree. Right is actually going to be 2. There's 2 good nodes in the right subtree, so 1 plus 1 plus 2, that's going to be 4. So from the root, we're going to return 4 good nodes in this entire tree. So with that being said, we can finally jump into the code. Okay, so we know this is going to be a recursive function, but in our recursive function, we're going to have to pass in more than just the root, so which is why I'm going to define a separate function inside of this function, DFS. Obviously, we're going to pass in the node or the root or whatever you want to call it, but we're also going to pass in what the max value is so far from the path, from the root all the way down to every particular node. And I didn't mention this, but our base case, of course, is going to be if the node we reach is null, right? So if not node. Now, what are we going to return then? Does an empty tree have any good nodes? Of course it doesn't, so we're going to return 0, right?
Oh, so he
okay,
does
so now
directly return it back up. I guess that's more efficient. I don't know if you can hear everyone, all of my residents, but I have no idea why, but I feel like my room, like, it sounds like my walls don't even fucking work. Like it's like my AirPods are on transparency mode. Like my room is on transparency mode. Like that's what it feels like. Like last year, my dorm, pretty soundproof. Like you can't really hear anything in the hall unless it was like directly outside. But here I can hear like everything. And Loki sucks.
we got to a node that is non-empty. We want to know, is this particular node a good node or not? Well, let's compute that into our result. So we're going to say, okay, result is going to be 1 if this node is a good node. How do we know if it's a good node? If the node.value is greater than or equal to the max value encountered so far. Otherwise, the result so far is going to be 0, meaning this node is not a good node. Next we want to do is update our max value so far, right? We're just going to take the max of itself and the max of the current node's value. So we've updated our max value so far. Why did we do this? Because of course we're going to need to pass this along to our DFS recursive call. Of course we're going to run DFS on the node's left child, passing in the max value. And of course we're going to do the exact same thing on the right child, the right subtree, passing in the max value so far. Now what are we going to do with the results of these two recursive calls? Well,
Add it. So return res plus DFS node dot left max val.
this function itself is just counting the number of good nodes, so we're going to take the result of it and add it to our result for both of these function calls.
Plus equals. How does that work in recursion? Like, how does the res variable stick? Oh, because every time you call a DFS, it's going to add to the original one.
Calls. We're going to count the number of good nodes in the left and right subtree, adding it to the result. Once that's been computed, then we can go ahead and actually return that result value. So you can see that this DFS, then we can go ahead in the left and right subtree, adding
What if no dot val is like greater than or equal to max dot max val? Res plus equals DFS no dot left.
adding it to the result. Once that's been computed,
Okay. Res plus equals DFS. Res plus equals DFS. Okay. Does it return res?
then we can go ahead and actually return that result value.
Oh, I like kind of get it, but I don't. I'm checking my briefing cause. Okay, we're good. Dang, I could have gone to the gym.
Function calls. We're going to count the number of good nodes in the left and right subtree, adding it to the result. Once that's been computed, then we can go ahead and actually return that.
Instead of doing like a global variable like this.
Result value. So you can see the entire tree. So when we actually can we pass over, but it's greater than or equal node. Actually, when you can see, it's pretty dang efficient.
Okay.
So this is a good fun.
These kids, man, it's 11 p.m. First day of school, and they're fucking yelling. Come on, bruh. And they never listen. Every time I tell them to be quiet and respect quiet hours. I really don't want to report them to my. I don't want to have to report them to my hall director, but if it comes down to it, I'm just gonna do it. It's fucking nuts. Um, validate binary search tree. I just sent a message to one of them. Hopefully it'll be fine. I mean, if not, I'm like low-key getting tired of it. I think I might just fucking report them to my hall director. Sorry. Can the root of a binary tree determine if it's a valid BST? So this is definitely a recursion problem. Both the left and right countries must be 33%. Holy shit. Holy fuck. How many more do we have? 2 more in here, and then 5 more here, and I'm gonna be caught up. Okay. gonna have that hold the parrot. If not, her empty tree is return true because it's valid. Still, empty tree is a valid PST technically. I think, at least. If it's not cur, okay, so if not cur, then return true. Otherwise, if cur dot, oh shit, but it depends if it's left or right. Fuck. Oh. No, that's disgusting. Okay, I'm gonna take a different approach. If not cur dot left. Turn true. Wait, fuck. Yeah. Okay. Oh. If cur dot bow is so if this is less than cur dot left or cur dot bow is greater than cur dot right, then we're gonna return false. Let's just do less than or equal to and greater than or equal to, else we return. No, else we recurse. So we have to recurse DFS. So you don't even need this. Self.dfs, self.dfs, cur.right. And right. You don't need this. So then we can call DFS on root. Oh wait, turn that. Oh shit. No. 6 out of 86. Fuck. Shaze. recur. How? Fuck. But I checked. Oh, no, I didn't. Huh? Holy shit, I was so close. Nope. Not again. This is not why I recurse. Oh. Oh, that is tricky. Okay, that is true. Only validate the immediate children. So how can I get the deeper one? No, but that can't be true, cause say I have like 5, right? 5, 4, 3. Let's make this 6 actually. So this would be true. But this can't, like this number can't ever be bigger than this. Because we already validated this is smaller than this. So if this other number is not smaller than this, there's no way it can be smaller than this. Oh, I'm confused. No, I'm so close. I think I'm gonna go ahead and watch the video. So around this is when I don't even know if I was thinking, but I definitely wasn't trying to actually understand it during all these problems. Holy fuck, I remember this shit was so annoying. Alright, let's just do this. And I think I'm gonna call it a night. Get ready for bed because I have class tomorrow.
Hey everyone, welcome back, and let's write some more neat.
Oh, it's only 9 minutes.
Hey everyone, welcome back, and let's write some more. Code today, solving validate binary search. A very good question for practicing binary search tree questions. We're just given a root of a binary search tree, and we just want to determine, is it a valid binary search tree or not? And from learning data structures and algorithms, you might know that a valid binary search tree is such that we have a node like 2, and every single node in the left subtree, 1, and if it possibly had other children, is going to be less than 2, right? So 1 is going to be less than 2. And similarly, every single value in the right subtree, 3, including 3's potential children's, if it had any, are going to be greater than 2. Not greater or equal, strictly greater. And we know this is a recursive definition, so if we had 3 and it had some children, like 5, and maybe 4 over here, we see that it's not a binary search tree because 4 should be less than 3. 4 should be less than 3, but it's not. So this is not a binary search tree. So we need to do a recursive depth first search to solve this problem, but let me show you what you might try. You might just try a simple solution like, hey, 5. We have 5 as the root. Let's check its child. Okay, 3 is less than 5. That's good. Okay, let's check the right child. Okay, 7 is greater than 5. That's good, right? Okay, now let's check 7 because we see 3. It doesn't have any children. That's good for us. We don't have to check anything. But 7 has a left child. It has 4 as a left child. Well, that's good. 4 is less than 7. And it has a right child, 8. That's good. 8 is greater than 7. So is this a binary search tree? The answer is no, because it's really easy to miss. We have a 5 as the root, we have a right subtree over here, and we have a 4 in the right subtree. But we know 5 is not less than 4. That's not true. So we need a better algorithm, and it requires depth first search. We can't just check the neighbors. So a brute force approach would be for 5, check every value in its left subtree, make sure that every value is less than 5, and then check every...
What I was... Fuck, I was only looking at the leftmost trail. Oh. Oh my goodness.
Value in the right subtree, make sure 5 is less than every value in the right subtree. And so we would need...
these descendants have to be greater than... Oh my god, wow.
N comparisons to do that, right? O of n. And then we'd have to repeat that process for every subtree. So 7, we got to repeat that, compare it to every potential descendant of itself, which is going to be O of n. And the time complexity of that overall is going to be O n squared. So can we do better than O of n squared? So one thing to notice is the root value can be any value, right? There's no restrictions on what the value can be because it doesn't have any parents. So we can say that it can be any value between negative infinity and positive infinity. And as long as that's the case, 5 is okay. We don't have to make any other comparisons. 5 is between negative infinity and positive infinity. Okay, and then when we go down to the left subtree, we know 5 is good. We don't even have to check it anymore. But when we go down to the left subtree, what do we have to check? All we have to check is that 3 is less than 5. So in other words, we just want to make sure 3 is greater than a negative infinity, which of course it is, and we're adding one more condition. We want to make sure it's less than 5. So our left boundary stayed the same, but we had to update our right boundary from up here, right? And so we're done with that. And of course, we don't have any children for 3 and 5. Of course, we don't have any children for 3, so we are done checking 3. Next, we want to also determine that the right subtree is a binary search tree. So we want to make sure 7 is greater than 5. But is there an upper boundary for 7? Like this could have been 100 or it could have been anything.
Infinity.
So there's no upper boundary yet. So we just need to check that 7 is less than infinity, meaning that this is the right boundary, and it's greater than 5. So we had to update the left boundary over here. When we went here, we only had to
Four
update
has to
the
be
right boundary.
less than 7,
And
but
this
greater
condition
than 5.
is true, so we
So
are
we only update the right boundary. Every time we go right, we update the right boundary. Okay, why the fuck does my AirPods keep doing that? Holy shit. Pissing me off.
done checking 7, it is satisfied. And when we go to the right child, 8, we're going to do the same, greater than 5. So we had to update the left boundary over here. When we went here, we only had to update the right boundary. And this condition is true, so we are done checking 7, it is satisfied. And when we go to the right child, 8, we're going to do the same thing. We only have to update the left boundary.
Wait,
The
I'm
right
getting-
boundary is a binary search tree. So we want to make sure 7 is greater than 5. But is there an upper boundary for 7? Like this, so is the right boundary, and it's greater than
Every time you move right, you update the left boundary. But every time you move left, you update the right boundary.
5. So we had to update the left boundary over here. When we went here, we only had to update the right boundary. And this condition is true, so we
So we
are
move
done
left
checking
again
7.
to 4. Then we have to update the right boundary to be 7. So it's 4 greater than 5 and 7? No, it's not.
It
So then we
is
return
satisfied.
false.
And when we go to the right child, 8, we're going to do the same thing. We only have to update the left boundary, so we have to make sure that it's left tree, but see what 7 it then 7.
Oh, that's so smart. Wow. It's for... What the fuck? Does it always look like that? So we return a left and right boundary. If cur less than or equal to left, or cur greater than or equal to right, then we return false. Well, I guess we do. If not cur, technically empty tree is true, right? Return true here. But if it's less than or equal to left, or cur is greater than or equal to right, then we return false. And then recur. To go left, we update the right boundary to cur. Then we update. To go right, we update the left to cur. Shit. Dot val. Oh fuck. What if it's null? Fuck. If we go left, we update the right. dot right, then we update the left. Oh, dot fuck cur dot val. Fuck. I think this is how you do it. Oh, fuck. Is that uppercase math? No. Fuck. No. Ah. Okay. I guess I just don't know how to implement it.
7, we have to update the right boundary for 4, but the left boundary stays the same. So we're getting the left boundary from over here. We're borrowing it from its parent because if 7 is greater than 5, then its left child, and 4 is a part of the subtree, 4 must also be greater than 5. So the left boundary is 5. Now, does this condition hold? It does not. 4 is not between 7 and 5. So this value breaks our binary search.
I could have just straight up used if not less than cur dot val less than right. Oh fuck, what did I do? No.
Tree. So therefore, this is not a binary search tree. It's false. We're returning false. And with this algorithm, since for each node, all we're really doing is making a comparison, we're making a single, or rather two comparisons. This is going to be big O of n, or 2n, which we know is still linear. So we can just call it big O of n. So now it's actually time to write the algorithm. And the best way to do this is recursively. So that's what I'm going to do. I'm going to write a helper function nested inside of this helper, or inside of our original function. We'll call it valid. We know we need to pass in the node since we are going to do this recursively. And we're going to have two boundaries, left and right boundaries. Like any binary search recursive function, if we reach a null node, we can just return. What are we going to return? We're going to return true because technically an empty binary search tree is still a binary search tree. And then we want to check, we want to make sure that node value is less than the right boundary and node value is greater than the left boundary. But we know if this is not true, if these conditions do not satisfy, then we have to return false because we found a node that broke our binary search tree. And now it's time to make our recursive call. So we want to make sure that the left subtree of node is valid, so we can pass node.left. And what's going to be the boundary for these? Well, since we are going left, we can leave the left boundary that a left subtree has to be less than every value. We know every value in the left subtree has to be less than the parent. And so the parent is going to be set to the right boundary because we need to make sure that this is going to be less than that.
My
so we
leg
want
is bleeding. I think I scratched a bug bite too hard.
Want to make sure that the left subtree is valid. We also want to make sure that the right subtree is valid. And in this case, we're going to do the opposite of what we just did. So the left boundary is going to be updated and the right boundary is going to stay the same because we know every value in a right
Well, don't you have
subtree
to
has to
check
be
left and right?
greater than the root or the parent node, which is the left boundary. And if both of these return true, then we can return true. If they both return false, then we can return false. So what we can do is just return the result of this. So whatever this evaluates to is going to be our result. We don't really need any variables. And now we just need to call the function that
What? I was thinking that. Oh. You don't have to validate cur.left and cur.right though? Am I tripping? I don't think so. What? It's still not working.
that we just defined, valid, we'll pass in the root. We want to make sure that this is a binary search tree. Initially, the left boundary can be set to -infinity.
Okay. There's no way. What? There's no way. There's no way. How come you don't have to check cur. Oh, we're not doing anything with cur.left.value. We're just calling it on the left and right. Oh my goodness. Oh my goodness. Oh my god.
Value could be, this is a super efficient solution.
Oh, fuck. That makes a lot of sense. Okay. So base case is true because empty is true technically. And we check if it's not in these bounds, then we return false. Otherwise, we recurse on the left and right because they both have to turn true, and then we update the left, or we update the right if we go left, and we update the left if we go right, and then we call it on the root with a -infinity. Bro, that's goofy as hell. Okay. Making good progress though. Okay. I feel so stupid. I feel like that one was easier to get than the count good nodes for some reason. Matter of fact, I'm gonna go revisit it just before I end this, so I don't forget. Okay, so essentially you're taking the max on a path, and if at any point the current node is less than the max, then we know it's false, right? Or I guess we know it's not a good node. So we only increase it when it's greater than or equal to the max, which is done here. Okay. I wonder. Okay, so we plus equal that. This was a bit. This section I feel like is a little confusing to me. Yes, you call it initially, so you have this variable and you add it equal to each other every single time. Return res. Okay. Okay. Sounds good. Okay. Okay. I think I'm just gonna leave it at that. We'll jump into k the smallest element and construct binary tree from pre-order and in-order traversal tomorrow. This seems what I'm thinking here is do in order, right? And return the index of the, I guess, length minus k. So return that index length minus k after we do in order and convert to an array. Okay, well, I guess I'll see you on the next video. I'm gonna wind down and then I might do a bit of schoolwork. I already have biology homework. Can't believe I'm taking it, but I'll see you all tomorrow. Peace.